Last time we said a redox reaction is a reaction that involves a transfer of electrons. And we said that if you can carry out the reduction and the oxidation in separate compartments, then we can get something useful out of it. We can get the electrons to flow through a wire, and we can use it to do electrical work. You can use it to light up a light bulb or move a motor. Okay, so a setup where you have the reduction and oxidation in separate places is called a galvanic cell, also known as a voltaic cell. My pen is not working. Okay, hold up. Okay, problem fixed. So, we said it's a galvanic cell, right? Or a voltaic cell. That's another name for it. Okay. So, as the reaction occurs in your galvanic cell or voltaic cell, electrons are able to travel, okay, through a wire. Okay, so the parts of a voltaic cell would be the anode, okay, half cell. Okay, so you can think, since a redox reaction involves oxidation and reduction, since we're separating them in two compartments, you can say why we have two half cells. Okay, so the anode would be one half cell, the cathode would be the second half cell. Okay, so you have two half cells. Like if you were to set something up like this in the lab, you would put two beakers. Okay, one, you have the reactant and product for the anode in one beaker. So let's call this the anode, and the other beaker would have the cathode. Okay, so normally you'd have a piece of metal sticking out of your anode. That could be part of your reactant reaction. Okay, it could be a reactant or a product, uh, and a piece of metal in your cathode, and then you hook them up with a wire. Okay, and you put a load here, or you can put a voltmeter here to monitor the tendency of the electron to go from one to the other. So a voltmeter would tell you the cell potential, also known as the EMF, or electromotive force. Okay, so that gives you a measure of the tendency of the electrons to flow. That tells you whether the voltage will tell you what the tendency of the electron to flow through the wire is. Okay. Now, to complete this circuit, you need to have something that would allow ions to move between the two compartments. So you have to have what's called a salt bridge. A salt bridge could be something as simple as a damp piece of paper. Like in the lab, we would use a filter paper soaked in an electrolyte solution. Okay, so it has to have ions. So your ions will be able to travel through your salt bridge in order to complete the circuit. Okay, so by definition, oxidation is defined to take place at the anode. So what we call the anode in an electrochemical cell, galvanic cell is also called an electrochemical cell. Okay, oxidation takes place at the anode, and the compartment or the half cell where the reduction takes place, we call that the cathode. Okay. A good way to remember this, O and A are both vowels, okay, just to help you prepare for the test. R and C, reduction of the cathode, R and C are both consonants. That's a good way to remember. Okay, so what we call the positive terminal of your galvanic cell is the cathode, and the anode is the negative terminal. Why is that? What do we know happens at the anode? Oxidation, right? What do we know happens in oxidation? You lose electrons during oxidation, right? So in an anode, then you would expect the electrons to come out of your anode. So that's why your anode is considered as your negative terminal. Okay? So in a galvanic cell, the anode is negative and the cathode would be considered the positive terminal. The electrons would travel through the wire towards the cathode, so the positive terminal is your cathode. So electrons travel from anode to cathode. Now, what about your ions in your salt bridge? How do they move? What happens when negative electrons come out of the anode? What happens to the anode? It becomes positively charged, right? In fact, what happens is typically you get cations. If your metal is a reactant in your anode, cations, metal cations will leave your metal. Your metal will get corroded, and it will positive ions will go into solution. So the solution becomes positive. So to neutralize that, what will happen? Your negative ions from your salt bridge will migrate to your anode. That's why we say the negative ions are anions. Anions in your salt bridge migrate to the anode. Okay? So the anions migrate to the anode, and your cations, the positive ions through the salt bridge, will migrate to your cathode. So again, it is easy to remember. A to A, C to C. Anions go to the anode, cations go to the cathode. And like I said before, historically the word battery refers to two or more galvanic cells put in series, but these days we generally just refer to even one galvanic cell as a battery. Okay? Your common household battery. Now, what would be the standard cell potential for this? If all your reactants and products are at a unit activity equals 1, your reaction quotient is equal to 1. The voltage that you measure is called the standard cell potential, right? So that's the standard reduction potential plus the standard oxidation potential. Or, since the numbers that you look up would all be given as standard reduction potentials, if you don't specify reduction or oxidation, you assume you're dealing with numbers you look up that are reduction potentials. So you say the expected voltage would be, under standard conditions, would be the standard potential in the standard reduction potential in the cathode minus the standard reduction potential for the anode, because you know what happens in the anode is oxidation, so you have to put the reverse of it, so you subtract. Okay, so you might see, depending on what textbook you're looking at, you might see the plus and the minus, just so you get things straight. If they're using subtraction, they're subtracting, then that means they're using standard reduction potentials for both sides. Okay, but if you're adding, then that means the potential for the other standard potential for the other compartment has already been flipped. All right. Let me see if I can show you there's a lot of really nice animations on the web that will help you visualize what's going on. And all you have to do is do a Google search for galvanic cells. Here, I've done one for you. Do a search for galvanic cell animation on Google. Okay, and this is what you'll find. Okay. One of the better ones, the really good ones, is a flash animation right here. Okay, I'm going to pause the recording here because I can't put this on YouTube because it's copyrighted. I don't want to be infringing. Okay, so let me... Alright, so in a typical AA battery, okay, you'll have one terminal marked positive, one terminal marked negative. Where does oxidation take place? Yeah. Huh? Yeah, I did. It's recording now. This is a galvanic cell. So, where would the electrons be coming out of? Got one more clicker missing. Okay. So, at the negative terminal, that's where oxidation takes place. Okay, oxidation takes place at the anode, and that's where the electrons come out. The anode is negative. Okay, so it's negative. Anode is negative. So in a galvanic cell, the anode is negative. All right, here's a good way to remember that the anode is negative in a galvanic cell. Anode. Cathode is positive in a galvanic cell, so cathode. All right. What would be our experimental setup for this reaction? What's our oxidation here? Copper becomes copper plus 2, right? So that's a loss of electron. So that means what? That's oxidation, right? So our anode should have what? It should have copper ions, right? And we're going to stick a copper metal in there. Oops, let me put this away right here. So you're going to have you're going to put up a beaker with copper ions. Now you cannot just have copper ions in there, right? It has to be copper something. So maybe copper sulfate, maybe. You can put a solution there. And then you would put a piece of copper metal there. Okay, that's your copper metal. That would be your anode. And then what do you do on the other side? For the cathode, what do you have? You put a solution of silver ions. So maybe like a silver nitrate solution. Okay. So silver with some other ion, negative ion along with it. And then you stick a piece of silver in there. And what do you do next? Hook these two up with a wire, right? And then run it through some kind of a light bulb or a resistor. That way you don't have a short circuit. Okay. You got a light bulb right there. Okay. But to complete this circuit, what would you need? You're going to need a salt bridge right here. Okay. So you can have like you can use like a piece of filter paper. You moisten it with an electrolyte solution. Or you can put an inverted tube there with a solution with cotton plugs on both ends. Okay, so that would be your setup.